Hello, my name is Neeti Parasher. I'm a professor of physics here at Purdue University Northwest. Um, I do my research in the area of experimental particle physics, also referred to as high energy physics. My specific research is at the Large Hadron Collider, which is located in Geneva, Switzerland. And the detector on which I work is called the compact muon solenoid, which looks for particles that can be predicted through the theory as well as particles that we have no clue exist in nature, but we haven't found them yet.
And I'm Eddie McGrady. I'm a student here at PNW. I'm a junior studying physics and mathematics. I did my work on the pixel system on CMS specifically. I was at CERN for 90 days. Um, Specifically, the pixel system, you have this is a scale replica of CMS. And because we're dealing with particles at such a small scale, we have to measure different states of the particle or different types of measurements of the particle with different detectors almost all together. So there's layers to CMS. We have first the barrel, which is where the collisions happen. Immediately out here, this purple section, this is our pixel system where it detects charged particles. It has silicon pixels inside of it where after a charged particle passes through it, where it triggers an electronic signal, and we're able to record that as an event. My work was I had a duplicate system of what's called the forward pixel. So the pixel's in two parts. There's the forward pixel here on the end cap, and then there's the barrel pixel which goes across the detector. And so my work was on the FPIC system. I had a duplicate set of parts in a lab where I would test how the effects of firmware and Pixel Online software on the system on measurement. Our collisions happen about 40 million times per second, which is once every 25 nanoseconds. So being very precise in the measurement of knowing when an event happens versus when we record it is extraordinarily important. And so I would run tests as to where I would know I can artificially inject charges. I knew how many charges I sent in. I knew the magnitude of those charges. I knew what pixels I sent them to, and therefore I could see probability functions of when I took it, how the magnitude of the charge, the density of the charge, the timing of when I decided to record it. All of that combined gave me ideal settings of when I would know if a charged particle passed through my pixel system that it would for sure trigger an event. This is extremely important.
There was a second student from Purdue Northwest who went. Can you tell me what his name is and what role he played?
Sure. So the other student we had was Christoper Perry. He's both a physics and math major and a senior student right now. He also worked and traveled with Eddie to work on the Pixel firmware stand that Eddie just described, but the work was actually completed in the desired fashion by Eddie at the very end of it. But I must add here that the pixel detector we have been talking about is really a state of the art technology because it uses these silicon devices that are extremely small. So the word pixel really means small. And these chips that we talk about are of the size of 100 by 150 micron, even though we call them square, but it's close enough. So precision is very important in all the experiments that we do, and there's no way we can lose data. So we have to be very specific where a charged particle through this detector actually passed through. So the segmentation is very fine. The whole detector put together has about 140 million channels that it reads out. So it serves really like a three-dimensional camera for us.
One of the things I also want to make sure that we bring out in this story is that you were part of the team that won the Nobel Peace Prize. So tell me a little bit about that.
Okay. So I lead the high energy physics program here at Purdue University Northwest. We are constantly every 3 years funded by the National Science Foundation. So this is a federal funding agency that gives us funds to carry out our research in terms of traveling, hiring personnel, and so forth. As a part of my regular work, which I do at both Fermilab and at CERN in Switzerland, in 2012 we discovered a new particle. We just called it a new boson until we could nail down its properties in 2013 and called it a Higgs boson, because then we knew a little bit more with the data that we accumulated. So the 2013 Nobel, not Peace Prize, but Nobel Prize in Physics went to the two theorists who actually had proposed the existence of the Higgs boson itself. So that was Peter Higgs and Francois Englert. And our group here with myself and my postdoc and students, we were all a part of this discovery. And my group actually specifically works on the on finding or searching for the Higgs in the data. There are several other areas one can do research in, but our group really specifically looked for that. So we were a part of that discovery. There were about 3,000 physicists from my experiment alone, and another about 2,700 or so from the other general purpose experiment called ATLAS on the Large Hadron Collider that collectively actually discovered the Higgs boson, or in the non-scientific community, the God particle, as we call it.
Thank you so much.
Thank you.